And today I'm going to discuss about ranks of a given transformation, which is also connected to rank of a matrix. So let's start the discussion because I have to go to college today also. Then therefore I have to be quick in discussing these things. So without further wasting time, then let's start our today's topic. And today I'm going to discuss first of all a definition, and the definition which I think you will not be able to find to digest, because already you have come across the results related to linear transformations. Now when a teacher teaches rank of a matrix in one hand and linear transformation on the other, I mean, if I could have taught you the rank of matrix first and then linear transformations next, then it would not be possible for you to connect those two things, because without letting you know about the linear transformation and going into the details of matrix theory, then what happens that we have to follow a different path for doing that. You will be confined to the matrix operations, and which you are familiar with, like row operations and column operations. And then suppose I am starting module 4 topics, linear transformation, etc. And if I want to connect a student with that, then every student finds it difficult, because he is already familiar with an approach and now he is going to get into the details of another approach. Now since the approach has been started with the discussion of vector space and linear transformation, now if I go into the domain of matrix, it would not be possible for you to grasp the ideas, because you already know that every linear transformation has its own matrix representations. Okay. And let me ask you one question and see whether you can answer to the question or not. If you have the answer, then you can write in the chat box. But before I ask you any question, I must tell you one thing, that you are mature students. Okay, so I know you know that nowadays every question solution is available in internet, Stack Exchange, for example. Now, if you type in something in Google, if you type something like Z, alphabet Z in Google, then Google gives you something. Okay, whatever. Google never says that, yeah, this is not known. Something is something comes pops up in the screen. Now, if I ask you any question, then if you go to the website to find it the answer to the given question, then maybe I mean, everybody wants praise. When a student is asked question, student wants to give it as soon as possible, so that teacher, he wants that the teacher must praise him. But what happens in online class? Is online class is different, because students often go to the Stack Exchange website and other website to get the results from there, and to he gets the result and he says it and types in the chat box, and thus he gets the praise. Okay, so that's not the way actually. So since I cannot see who is doing what, and it's not a competition, it's a classroom, it's a discussion. So if you, even if you answer, you will not be praised. I'll just say, okay, thank you so much. Okay, so whatever say you say it from your mind, by thinking it, because you're learning maths. So you just say it. Don't Because if you say something of your own, that is your originality. So if you can apply your originality to the subject matter, then only reply. You are expected to reply. If you are getting answers from here and there, or by WhatsApping each other, then yeah, you can discuss among yourselves. uh, that is is a good, I mean, I appreciate that. But if you are getting the solution from the internet, then that is not a good approach. So therefore, just if you have the answer with you, you can write in the chat box. My question is just a question. It's just I mean, my as per my today's topic, it has nothing, it is not that important. I mean, important in a sense that understanding is important, but if even if I do not ask this question, that doesn't really matter. But yet I want to ask this question uh, because I think it is important. We know that linear transformation, every linear transformation has its matrix representation. And every matrix can be connected to a linear transformation. So it's both way true. But my question is, suppose you have a linear transformation T from the vector space V to vector space W. How many matrix representation does T have? That is the question. Question is, how many matrix representation will T have? So let's see who says what. I mean, if you are thinking about number, I mean the value. No, don't think about, I'm not asking you any formula. I'm just, you can give your answer to, you can give your answer in sentences. To derive, to get formula is very difficult. I mean, how you're writing m into n, I don't know. Without any thinking, you are writing that. No. No, dimension V means n. That means if V has a basis, then number of elements present in the basis, that is the dimension. So you are actually talking about how many elements are present in a basis. I'm not talking about that. I'm talking about how many matrix representation will T have. You can reply in sentences. You don't have to give me any formula. Yes. Someone has written something. Let me see. Okay, thank you. Now, the thing is that the correct answer is T will have matrix representation T will have different matrix representation which depends on what basis or bases you are working with. I mean, if you are working with basis beta and gamma, you are going to get one matrix representation. Now, if you are considering basis beta prime and gamma prime, you are getting another matrix representation, and so on. And I think there is no such formula which gives you that how many bases will there be for a given vector space. Vector space can have many bases, and bases can also be constructed. I'm saying that from the by using the theorem which is called extension theorem. So you can construct basis also. So therefore, depends upon how many, what basis you are working with. On the basis of that, actually, uh, you are going to get different representations of the linear transformation. Okay, so that's the thing. That I just wanted to know from you. Probably it has something to do with my today's class, and probably not. So let's not discuss about this right now. Let's go into the details of my topic. And my first definition, which I'm taking from the book, is goes like this. Definition is, if capital A belongs to M cross N F, we define we define the rank of A, which we denote by rank J, denoted by rank A, simply denoted by rank A, to be the rank of to be the rank of the linear transformation this. Now, probably you all are familiar with these expressions. You know what LA is. LA is kind of this thing. Okay, probably you can remember, and you also know this about this vector spaces Fn and Fm. Okay. Now, so it's just a definition. I mean, this definition is actually is not working. I mean, this is not a working criteria. Every new concept has a definition, and along with that definition comes the working criteria. I mean, if I give you any linear transformation, then at least you know that if you can find the matrix representation of that linear transformation, then rank of that matrix representation uh, is will be equal to the rank of that linear transformation. But how to find the rank, that I have not yet told you. Just with respect to this definition, immediately a theorem can be constructed, which is there in the book. I'm writing the theorem also for the sake of your understanding. But none of this theorem, it's a, fortunately in this particular chapter 3.2, none of the theorem, you don't have to prove any theorem. Just get the results, and wherever applicable, you can try to use that result. Okay, so we shall not try to prove those results. Let capital T is a linear transformation from V to W be a linear transformation between finite dimensional vector spaces, finite dimensional vector spaces, and let beta and gamma be ordered bases, be ordered bases for V and W, for V and W, then respectively, respectively means beta is the ordered basis for V and gamma is the ordered basis of W. If I do not write the word respectively, that means somebody may think that beta is the ordered basis for W and gamma is the ordered basis for V. So it is always, this word respectively is supposed to be written always. If I write the line in this particular manner, then rank of the linear transformation is equal to rank of this. You know, T beta gamma is the matrix representation of the linear transformation. If you can find the rank of this, then rank of the linear transformation can be found. Now, here I want to discuss something, and I'm going to the next page. If you have not copied, don't worry. The, the result is there in front in the book in section 3.2. You can get it from there. Okay. You can write only this thing, and the other sentences you can construct by yourself. Question is, I mean, the beauty of this particular theorem is that probably you are, I'm writing the theorem once again over here. Rank of T is equal to rank of T beta gamma. Okay. So probably you are thinking that, yeah, it's obvious. Rank of T is equal to rank of T beta gamma. Obviously, if T has a matrix representation, then this, if you can find the rank of this matrix, then it would obviously be equal to the rank of the linear transformation. But if you think very deeply, you can recall one thing, that during one of my sessions, I told you that rank of a linear transformation is actually dimension of the range space of T. And also you can remember that there was one result which goes like this: nullity equal to T, that is the definition. It is the dimension of kernel of T. Okay. Now when we find when a transformation is given and we try to find the rank of T, if I stick to this definition, then I need to find a range space of T, and from there I actually uh, try to count, and you know that if there was a result, you have to consider the basis, the span beta, etc., etc. Many things we have to do, and after that, after several calculations, we need to find, we have to find the rank of T. Sometimes it becomes very difficult to uh, obtain directly, so we can also use the dimension theorem. The dimension of V is equal to nullity of T plus rank of T. So it happens once, it happened once that one of the students, he gave me a problem, and he couldn't find rank of T, but he could find nullity of T, and dimension of V was known to him. After putting these results in the formula, he was able to find rank of T, but he later asked me how to find rank T directly, because that problem became very difficult, and to understand the range space of T, it was also very, I mean, was very difficult to understand for that particular problem. So now you look at this theorem. So if you can prove, I don't want you to prove this theorem, but if you know this particular result, that rank of T equal to rank of T beta gamma, whatever the linear transformation is, you know that if you can find, uh, it is far more easier to find T beta gamma, this matrix representation T beta gamma, than to find RT. Okay. I don't know whether you are agreeing with me or not, but I think T beta gamma, finding T beta gamma is far more, uh, uh, I mean, finding T beta gamma is far more uh, easier than to find RT. And therefore, if you can find T beta gamma, then somehow there are some working criteria by which rank of this matrix representation can be found. And that matrix representation, the rank of that matrix representation will be equal to rank of the linear transformation. So actually, you don't have to use this result. Actually, you don't have to use this result at all. So that's why the result is very powerful. Okay. Now, once we know that the matrix representation rank can be found, the question is, what is rank? What is rank, and how to find it? What is the working criteria? What is the working criteria to find rank? Okay. What is the working criteria to find rank? So there is a working criteria which goes with which actually goes with by a theorem, the theorem which I'm going to write below. Just a minute. One of the section B student is actually SMSing me. Just a minute. The rank of any matrix equals the maximum number of its linearly independent columns. Linearly independent columns. Okay. So that is called the rank, and another line is written after that, that is the rank of a matrix is the dimension of the subspace generated by its columns. So the rank of any matrix equals the maximum number of its linearly independent columns. And you know what linearly independent column is. So you can consider this example. A is equal to 1 0 1 1 0 1 0 1 1 1. Suppose this is a matrix representation corresponding to a linear transformation, and carefully if you observe to this particular matrix, you will find that suppose this is my column 1 and this is my column 2 and this is my column 3. You can observe that column 3 can be obtained if we add column 1 and column 2. So actually column 3 can be expressed as linear combination of with some scalar 1 into C1 plus 1 into C2. Okay. Now this I mean, what it means? It means that C1 and is dependent upon C3 and C2 is dependent upon C3, but no way you can generate C1 from C2. C1 cannot be expressed by C2 and vice versa. So what does it mean? This implies that this column C1 and C2, they are linearly independent, and this implies that rank of A, since the theorem says that it is the maximum number of linearly independent columns, then rank of A is equal to 2. Rank of A equals to 2. Okay. So see, I mean, by using this particular theorem, we have found that this rank of the given matrix is 2. And if you say that capital A is connected to a linear transformation T, then you can say from here that T is the linear transformation, some linear transformation. Then you can say that rank of T is also equal to 2. So what I'm saying, that if a matrix is given to you, then this matrix is actually using this theorem, that number of independent, maximum number of linearly independent columns gives you the rank of the matrix. And since we know that it comes from the definition, that rank of the, not definition, this theorem, that rank of the matrix representation of the linear transformation is equal to the rank of the transformation. So since rank of the matrix has come out to be 2, so if capital A, you think that it is connected to some linear transformation T, then rank of T will be exactly equal to rank of A. The rank of A and rank of T will be same, and that the value will be 2. Okay. So this is the usage of this particular theorem to the given, I mean, problem. Now, it is not often possible for us to find the rank of a matrix so easily. We cannot, what was I saying? Sorry, actually, one of the student is SMSing me, and therefore it is distracting. So I was saying that if you can find the matrix representation, and if you can find the rank of that matrix, okay. How did I find the rank of the given matrix? Just looking at it and seeing that, yeah, it is the matrix representation. This matrix representation, in this matrix representation, the number of columns, these two columns are actually independent, and these two columns are dependent on C3. So C3 is actually, I am redundant. C3 becomes redundant, and then I am counting the maximum number of independent columns, and that is your, I mean, 2. Also, you can say that, yeah, you can say that you cannot C1 and C3. If you don't take only C1 and C2, if you consider C1 and C3, then also you see that C1 and C3 are linearly independent. Okay, or if you say C2 and C3, C2 and C3 are linearly independent. So I must write this. Otherwise, you may think that this is the only possibility. So in this matrix representation, in the previous case, number 1, C1 and C2 are Li. Number 2, C2 and C3 are Li. And number 3, C1 and C3 are Li. So both of these, all of these pairs are actually Li's. Okay, but you cannot say, we cannot say that C1, C2, C3 taken together are Li. It is not true, because C3 is actually the linear combination of C1 and C2. Therefore, they have said that maximum number of linearly independent columns is 2 in the above matrix. Okay. Now, it is not always possible for us to analyze the situation so easily, because the matrix is written in such a way, so many non-zero values are given, that immediately by looking at the matrix, it will not be possible for you to immediately say that, yeah, these are the linearly independent columns and those are the linearly dependent columns. So we have to do something extra so that we can get some information about linearly independent columns from the given matrix. This theorem is always not helpful for any matrix. For some matrix, it becomes helpful. So what do we do? So if it is this is the scenario, what do we do then? So there is a theorem in the book which says that it's not actually a theorem, it is the corollary to a given theorem. I'm not writing the theorem, but I'm telling you the number of the theorem which is there in the book. The theorem number is 3.4, and I'm writing its corollary to theorem 3.4, and it says that elementary row and column operation on a matrix are rank preserving. So can anybody have any idea about what do we mean by this word rank preserving? Elementary row and column operation on a matrix are rank preserving. You already know that what is elementary row and column operations. What are the elementary row and column operations? Yes, rank will not change. So if I transform a matrix from a given, if I transform a matrix to another matrix, okay, suppose after elementary row operation, a matrix is transformed to another matrix B, okay, then rank of this matrix will be exactly equal to rank of that matrix. Okay. Question is, why should we transform? because sometimes the matrix is given in such a manner, so it is not possible for us to immediately tell what will be the rank. So we apply the elementary row operation on it, and we try to find out the rank of the transformed matrix. And due to this theorem, since elementary row and column operation preserve rank, so we can say that since the rank of the transformed matrix is this, rank of the original matrix from which it was transformed is also this. Okay. Now you already know that what is elementary row and column operation. Elementary row and column operations are of three types. First of all, we can interchange any two rows or any two columns, or we can multiply any row or column by scalars, non-zero scalars, or any scalar multiple of a row or column can be added to other row or other column. Okay, these are the elementary row and column operations. So by keeping this in mind, let us take another matrix which goes like this: 1 1 1 2 0 1 1 3 2. Okay, so I am going to apply the elementary row and column operation over here. Immediately by looking at this, you will not be able to tell what is actually rank over here. Okay, so I have to transform this matrix. So my job is to transform A by applying elementary row and column operation. Elementary row and column operation. Okay. So, and whenever you transform the matrix, if you are going to write another matrix, put this sign. It is called tilde. I have said earlier also. This tilde means equivalent to. So let us try to find out a form. Let me not talk about the form right now, right at this moment. I shall talk about it later on. First of all, let us do it. Okay. So here I am keeping R1 as R1. So R1 is not getting changed. Okay. And I am subtracting R1 from R2. So I'm writing R2 equal to R2 minus R1. And I am subtracting R1 from R3 also. So what do I get? I get 1 minus 1, 0, 0 minus 2, that is minus 2, and 3 minus 1, that is 2. And 1 minus 1, that is 0, and 1 minus 2, that is minus 1, and 2 minus 1, that is 1. Okay. Then I'm going to do a column operation. What is that? Column 1 will remain same. Column 1 will remain same, and from column 2 can be changed in the following manner. I can subtract twice column 1 from column 2, and I can subtract column 1 directly from column 3. So what do I get? I get 1 0 0, and that will be twice of this will be subtracted from column 2. So 2 minus 2, that is 0, minus 2 minus 0, that is minus 2, minus 1 minus 0, that is minus 1, 1 minus 1, that is 0, 2 minus 0, that is 2, 1 minus 0, that is 1. Okay. Now this much have been done in the book. I shall proceed a little bit further. Okay. I can discuss this in the next session because this session is going to end very soon. So after that, what will I do? I will keep this matrix 1 0 0, and you see, I can what I can do. I can fix R1 as same, and this R2 can be changed to R2 minus 2 R3, R3 minus 2 R3. So if I multiply R3 by 2, I will get 0, minus 2, and 2. And if I subtract from R2, what do I get? 0 minus 0, that is 0, minus 2, minus minus 2, that is 0, and 2 minus 2, that is 0. Okay, and let us keep it same, no problem for the time being. Then what can I do? I can go a little bit further, and I can keep the column 1 fixed. I can keep the column 1 fixed, and column 2 and column 3 can be added together. Okay, so what I am changing, as I told you in my last class, so you have to be careful enough to write. If you are adding two columns, you have to write it in this manner. I want to change column 2 because minus is there. So I must write it in this way: C1 minus minus C3. Okay, so that becomes, that actually changes C2. C3 will remain same, and we can write it as 0 0 0. And then what I can do, I can interchange these two columns. So C2 and C3 has been interchanged, and then I can interchange the two rows. So R2 and R3 has been interchanged. Now you see, look at this representation and that representation. Clearly you can say that these two columns are linearly independent columns. These two columns are linearly independent columns. So if we name this matrix as B, so rank of B is equal to rank of A is equal to 2. Let's discuss about this in the next session. This session is going to end.